hear this many times to understand something. Yeah.
Yeah, so recording is on, so let's start.
Yeah. Okay.
I'm sorry, I didn't catch that last part.
Yeah. Just we started the recording.
Oh,
This was
cool.
the information.
Yeah, and let's start the talk.
Yeah.
All right.
Let's start now. Slowly.
Okay, so well, thank you for inviting me. So, um, we talking about some work uh, that happened a couple years ago on the so-called dimension spectrum of lines, and throughout the talk, I'm only going to be dealing with plane, so I'm dealing with R2. Um, So, just to recall some of the definitions that Sasha went over, I guess 2 weeks, 3 weeks ago, maybe. Um, so, if I have, let's say, a real number x between 0 and 1, and a precision r, and when I say precision, I'm always going to mean a natural number. The Kolmogorov complexity of x at precision r is, so this is just the usual Kolmogorov complexity of the first r bits. So this is the first r bits of x in its binary representation.
Which is the same as a minimal complexity of rational approximation with precision 2 to the minus r up to some logarithm or whatever.
Right. Yeah, there's a lot of equivalent definitions that are the same up to a logarithmic error. So
So you
closest
shouldn't be
rational.
afraid why it's binary representation, maybe not ternary, and not, it's just very robust thing.
Yeah. You could also say that it's the closest dyadic approximation at precision
Yeah.
to the negative r.
And
So
if you take sine of this x, it will have the same precision also.
correct. Yeah. Any way to computably represent x up to precision r, it's all the same. Um, so let's see. Okay, this is for reals in the unit interval, but you can extend this easily. So you can extend this to points in R and then to points in Rn in the usual way. So for a point in R that's not necessarily in 0, 1, you just have to give the finite number of bits saying how big the magnitude of x is, and then give the binary representation. For Rn, you have n tuples of these things. So I don't want to spend too much time, but if anybody has any questions, feel free to stop me.
No, I guess this should be clear.
Okay, so yeah, and like I said, the logarithmic errors, in fact, sublinear errors, we don't really worry about too much for the following reason. We're most interested in the effective dimension, the effective Hausdorff dimension of Euclidean points. Let me just remark this is effective Hausdorff, which is defined to be the limit inferior of the Kolmogorov complexity of x at precision r divided by r.
Yeah, and there is a strong dimension which is lim sup, and something different happens with it. But now we have this lim inf.
Yeah, right. We can also talk about the effective packing or the effective strong dimension, which is just the dual. This is also an interesting notion. It corresponds to packing dimension. So it is used, but in this talk I won't need it. Okay. I guess the last definition I wanted to give for now. So we're going to be talking about lines in the plane, and so there are many ways to parameterize lines. We'll use the usual point line duality. So let LAB be a line in R. So this is a line with slope A, intercept B. Let's see, the Kolmogorov complexity. Complexity of the line at precision R is just the Kolmogorov complexity of the pair AB. So we're just parameterizing lines, non-vertical lines by Euclidean points in R2 in the usual way. Okay. So the main
dimension is defined in the same way.
Yeah. And then of course the dimension of a line is the dimension of the pair AB. Yeah. Okay, so the main object we're going to be studying is something called the dimension spectrum. So let's see. So the dimension spectrum of a line, L is all the possible effective dimensions, all the possible values of the effective dimension of points on this line. Okay. So we're looking at this set. And the conjecture posed by Jack Lutz in the early 2000s was that for any line L, the dimension spectrum of L contains a unit interval. So
if L has dimension greater than 1, is this interval between 1 or 2 or some other?
So yeah. So notice. Let's do some remarks here. So first of all, since we are in R2, the dimension of any point in the plane is at most 2. We have an absolute upper bound on any point in R2. Exactly from the definition, right? To describe a point to precision R, it takes at most 2 R bits plus a log
And
term.
also L plus 1.
Yeah. And then the other upper bound, so since, and you can check this immediately. Since the complexity of a point on the line is at most the complexity of the pair x and the line, and since each term, so the complexity of x is at most r, and the complexity of the line well, let me do it this way. Since we have this inequality, it's not hard to verify that the dimension of any point on the line is at most 1 plus the dimension of the line.
So even if A is great number, we lose only finitely amount of precision when multiplying AX to plus B. So for in the limit, everything is okay.
Right.
I'm a little bit lost. I confused what is x plus b. What
It's
is
a point on the line AB. It's arbitrary point on the line AB has form X and AX plus B.
so? What is how CR is defined?
For 2 real numbers, there are first R bits of each. First R bits of each.
Complexity of the pair of the first. So you take
Yeah,
you
just
take
precision complexity of a point up to precision R. Yeah.
no, but you have 2 points.
No, I have
How
one
it's defined?
two-dimensional point.
You compress them into one number and take the first R.
No. We take R bits from each coordinate. So it could be maximally 2 R bits. Maximum of this complexity is 2R.
So I guess the question is, so the complexity of these real numbers is just the complexity of.
So is it very clear all these explanations sorry, so so you say that the complexity of any point on the line is at most 1 plus dimension of the line.
Complexity of the line. Not
But
complexity.
so I mean, I guess you say like take the x coordinate or something and then describe the line, and it defines your point.
Right.
But
Yeah. What is missing is
But
just one coordinate.
wait, but for stupid people, can at least some one sentence be said what happens with the precision of numbers? I mean, it's supposed that I've defined it exactly. I mean,
No, if you have X, if you want R bits of AX plus B, then maybe you need R plus constant bit of X. If A is large number, then you need some better precision. But since it's only constant number of bits, it doesn't matter in the limit.
no, wait, I don't understand anything.
Just okay. Just say.
It cannot be said somehow. So once again, the dimension of the line A is like the line is given by 2 coefficients, A x plus B.
A and B, yeah.
A and B.
And so you say if I know the first R bits of A, the first R bits of B, and the first R bits of some number X.
Then you know the first R minus constant bits of AX plus B. Plus minus some.
Yeah, I mean, and you want to say that, okay, maybe A and B also have some, I don't know, some integer part, but it's a constant.
Yeah. Because of this integer part, you maybe need more.
Yeah, so multiplication. But wait, when I is it like more than enough if I like take more than we need, because when I multiply two numbers that are like with r bits,
Yeah.
then the length then that would be like two r bits after. So maybe I need just r plus two.
No. If A is big like 1,000,
Yeah.
then r bits of x needs r plus 3 bits of x. That's the simplest thing which we are trying to say.
So you want to say that okay, so if you know a and x with precision 2 to the minus r, so you know the product more or less with the precision 2 to the minus r up to some constant.
Times the maximal absolute value
Times.
of A and B plus something.
Yeah. Okay, maybe. Okay.
How is that?
Yeah, that's fine. Just wanted to get used to this explanations with precisions. Okay, it seems
No, but
fine.
actually, the direction of inequality should be different.
The other way. Sorry.
But still,
Well,
it's still okay. But there is some. No, actually, there is a more subtle thing. If you want to measure precision, not dimension, but something with finite precision, it's better to consider line in projective space and consider the epsilon approximation in projective space. It will be more uniform then. But for if we are worried about dimension, it's not a problem at all.
Okay.
Okay, so now we can prove the conjecture or what?
yeah. So let me see. So okay, well,
Or some part of it.
yeah. If you're interested in the history, so there was some partial progress about this question, but maybe we can just get into the main result, which proves that this conjecture is true. So let suppose I have a line in R2, and I can of course assume that the line isn't vertical. A vertical line clearly satisfies the dimension spectrum conjecture, right? Yeah. So I have a non-vertical line in R2. Then
Should we understand this, or it's will not be important? I mean, I don't know why.
No. We can understand.
Oh, okay.
Vertical line.
Yeah. So
Vertical line is just a pair of points. The first coordinate is taken from the line, and the second coordinate is arbitrary point. So the complexity of the pair is just can be anything. We add to the complexity of the first bit of the first coordinate any number. It's important to understand now. Yeah. Let's do it.
Yeah.
So-
But let's try. Okay, you say that if I have a vertical line, how it's
Yeah.
defined? So it's
No,
in
vertical
how
line
it's
is not
complete.
formally line ax plus b, but its complexity is the complexity of
The intersection with
coefficients
the
of the
x.
equation, which
Yeah.
is just the complexity of the first coordinate of the line.
And you say that you can add any number.
If we take a point, we fix the first coordinate and add any second coordinate. So we take a fixed point x and add any point to it. And in this way, we can make complexity up to r up to something to. We just add r in the complexity from 0 to r, and in dimension we add something from 0 to 1.
Independently, something independent from this.
Yeah. We need to conditional complexity of the second coordinate with the.
So I don't know. Let's just if I pick each bit with some probability, then the complexity.
You can construct a random sequence in different ways. Just it should be random with respect to the first coordinate.
Yeah, I mean,
So how to construct a line of a point of any dimension? Just take a random sequence and then dilute it by zero sum in proportion you want.
Yeah, okay, it's more or less clear.
Yeah, yeah, yeah.
Should I explain?
No, I guess you can continue with the theorem.
Okay.
I think Sasha is satisfied now.
Okay. Yeah. Um, so if I have a non-vertical line in R2, then we will show that the dimension spectrum contains the unit interval d to 1 plus d, where d is equal to the minimum of 1 and the dimension of the line. And as we saw before, this is the best you can do. This is the absolute maximum of the dimensions of points.
And by the way, do we know something about the other part of the dimension spectrum? What happens below D?
Yeah, we do. We have some partial progress in this. I think full understanding. I mean, given a line, given a line and a number alpha, we don't yet know the dimension of the size of points whose dimension is at most alpha. So it's not completely known, but there's some partial progress.
But at least probably you know that the spectrum is not determined by the complexity of the line and could be different from the lines of the same complexity. Yeah.
Yeah. So it's a much more subtle question. When you get to the lower end of the spectrum, this is much more subtle. If you want, so maybe I'll just put this. I'm not going to really talk about this, but we also know that so the Hausdorff dimension of the set of X such that the dimension of the points on the line is smaller than the dimension of the line divided by 2 is 0.
Okay, so it's next level of sophistication. We study not the spectrum, but how often some number appears. Okay.
Yeah. The spectrum's hard. I would guess that the spectrum can be totally disconnected below D, but not sure.
Okay.
Okay, so I think I want to start. So we're going to start with a warm up to introduce some of the techniques. And the first part is a purely geometric lemma, which I'll then rephrase in terms of Kolmogorov complexity. But maybe the picture is the best way to start. So let's say I have two lines. Okay, this is LAB, this is LUB. Okay, so A is the slope of the first line, U is the slope of the second, and the kind of the elementary school geometry that's underlying a lot of these things is just the fact that two lines determine a point. That's the level of sophistication that's going on in geometry. We are doing something.
In combinatorial case, we use this for the formula of inclusion and exclusions to estimate the scalability. But here something different happens.
Yeah, and in the finite field case, we were able to exploit this exactly because we were dealing with finite objects. The one wrinkle we have now is that we're not dealing with absolute objects. We're dealing with approximations of lines. In other words, we're dealing with 2 to the negative r neighborhoods of lines, which are just strips. So maybe I'll draw. Okay.
So this is our neighborhoods in the space of AB, in the space of coefficients.
Right.
No, so it's a bit misleading that they are parallel. You allow also to change A.
Right. Yeah. So we're So you should imagine that we're shrinking the microscope to something close enough that these do look like lines. In fact, they're more like cones. But
Okay.
but okay. So the main question is, so these are 2 to the negative r approximations of lines, and the main question is, if I give 2 approximations of lines, to what precision can I determine their intersection? And if you think about this, what we're really asking for is what is the diameter of the intersection of these 2 strips?
No, it obviously depends on the difference between A and U, and it should be in the denominator, and otherwise it's more or less constant.
Right. Yeah, exactly. So this is completely determined by the angle these lines are making. So let me write this. This is up to a constant, depends on where they're intersecting, but this is essentially 2 to the negative r minus t, where t is negative log of the distance AB minus UB. So this quantity can be interpreted in 2 ways. This is the angle between the 2 lines. And it's also the number of bits AB and UV share. Number of initial bits, I guess, is important.
No, I think there is some technical problem because, for example, if A is very close to U and B is different from V,
then they don't intersect.
No, they don't intersect in our region. They intersect far away, and we do not say anything about this.
So yeah. So I'm assuming. So let's assume we're dealing with
points in some bounded region or something like this.
Yeah. So we're dealing. Let's say we'll always deal with some region n to n. Some of the squiggly approximations, this depends on where they're intersecting in Rn. We'll always assume that they're intersecting in some bounded region. It turns out we can always do this because the initial integral describing the initial integral point of the x is irrelevant for us.
You have a system of 2 linear equations, and the standard problem is it can be not, I don't know how to say it in English, well determined or something like this.
Right.
The inverse matrix.
Sasha, so you understand this well? Sasha, Shane.
Yeah, I think just philosophically, yes. Yeah.
Well, I'm not, so maybe, I don't know, maybe. So, I mean, let me try to at least understand the claim. Let me try to more or less understand the claim. So if I know A and B and U and V with precision R, the claim is that, well, I mean, the weak version of the claim that I know the intersection Wait, I don't know even in which sense. The diameter, no. So it's not that I know the points with up to more or less r bits. I
So
somehow
if the angle is small, you lose precision. That's what it.
no, but I see here that the precision is at least r. It could be even better, but let's maybe at least understand that it should be r.
No. It's worse than r because it's r minus t.
Wait. So
diameter we lose precision if the lines have a very sharp angle inside.
but the precision, so it's not that I know the intersection of the two lines up to some like their coordinates up to that many bits. It's just I know the radius. I know somehow or
No,
no.
but of course you know there are coordinates up to that many bits approximately. Why? If you know the diameter of the intersection, it's small, then you take just 1 point of the intersection.
Yeah, okay. So the claim is that I know with some precision.
Yeah.
And there is some geometric explanation of this.
No, yeah.
Or some kind of algebraic, I don't know. I mean, because I can solve a linear.
We can solve the linear system, and if it's numerically stable if the inverse matrix has not a big norm. But geometrically is much easier. Imagine we have two lines which intersects with some reasonable, not very small angle. Then if you shift a bit each line, the intersection point doesn't move significantly.
Yeah, the way.
Yeah. And if they are like very small angle, then you say.
Of course, if angle is very small, then shifting one line a bit, we can move the point along the other intersection point, move along another line for a long distance. So that's why we need some.
I can't imagine this, but I don't know. I think.
I can say in Russian, если ножницы пересекаются под малым углом, то точка движется быстро. If you take the scissors and the lines you start to cross, then the point goes very fast.
Yeah, I don't get it.
Okay, if lines have small angle of intersection and you just shift one line parallel to itself, then the intersection point.
No, I mean you're claiming this. I mean maybe I should imagine this, but I can't do this in the moment, so I don't know. Maybe we should just believe in this geometric fact and continue.
No. Probably there is some misunderstanding. So imagine we have two lines, and they are very close, almost parallel. They intersect with very small angle.
Well, parallel, I imagine that they intersect somewhere very far already. I don't know.
No. They intersect here, but with a very small intersection angle.
Yeah.
And imagine we now move one line parallel to itself a bit.
Yeah.
Then intersection point can move significantly because the angle is small. No, just maybe if you can.
I mean, it's hard to imagine a bit in which direction a bit. I'm imagining that I'm taking one point line across the other line a bit, and so the intersection point moves a bit.
I cannot draw, but I would draw lines which cross with a very small angle.
I'm sorry. We have a geometric lemma on the screen. Maybe it's better to understand it because the previous geometric illustration is just an illustration. We need some quantitative statement.
So let's see. So the geometrical statement is that if I have two strips, the diameter of the intersection of that strips is completely determined by the angle between the two lines. and it has a very nice form that the diameter of the intersection is up to some multiplicative constant 2 to the negative r minus t, where t is the angle between the 2 to the negative t is the angle between the two strips. The way you can, so this is the geometric idea. You actually prove this, you can just use algebra, the system of linear equations. If ax plus b is equal to ux plus v, then the intersection is given by the difference between v and b and a and divided by a and u. If you do some calculation, you'll see that knowing a, b, u, v to precision r, in other words, knowing a rational within 2 to the negative r of all four quantities gives an approximation x prime such that x minus x prime, x minus x prime is smaller than, up to some multiplicative constant, 2 to the negative r minus t, where t is the difference. Is that at least...
Sasha, do you understand what is happening, or some thing is needed?
I guess I understand the statement. So this algebraic form is like clear. So I have v minus b divided by the difference of a and u. So I don't quite understand why the precision, like this t depends also on b and v.
We're assuming that they intersect in some bounded region. Let's say, you fix the unit square.
No, actually, it doesn't depend. It's actually but for the bounded region, the difference between a and u and v is more or less the same.
Right.
If they intersect in not far away.
So we have v minus b, so we know this difference up to r bits, but we divide by a minus u, which can be a small number, but when we multiply it, so I would understand probably this statement if t was the number, it was probably before, the first, the number of bits where a and u coincide. But I don't understand how v and b are involved here.
But it's exactly the same. So imagine two lines intersect at this point at an angle theta. Then the distance between the y-intercept is roughly theta, as long as I'm in a bounded region.
Yes.
And that's all I'm saying.
Okay, so the difference
between A and B is roughly the same as the difference between U and V. It's the same quantity. Up to a multiplicative, all this is...
Okay. Okay. So wait, so once again, the distance between the intercepts up to multiplicative constants is the same as what?
Is the same as the angle.
Is the same as the angle.
Which is the difference between the slopes, yeah. All these things are...
between the slopes. And the slope is just the difference between A and U. So the difference between A and U is basically also the same thing as the difference between B and B. Okay, yeah. All right. I think it's I believe it now, more or less.
Do we all believe? Let me ask maybe this geometric lemma then, assuming the geometry, the algebra is okay, we have immediately this geometric lemma. It's really that fact in the language of Kolmogorov complexity. If I know AB and I know UV, then I can compute their intersection up to precision R minus T.
Yeah, for me, it seems that I understand everything, and this is suspicious because the result itself is mysterious, and so mystery is
No,
postponed to
I mean,
something.
Sasha,
But
just you have to live with the fact that maybe that not all people are that smart and fast as you. So
no, it's not.
uh,
Okay,
we are
That's not
sorry that we
false.
couldn't keep up with you, but we are trying. So
Okay.
okay, yeah. I mean,
Is
so
there
if
any
I know,
question now?
so
Let's ask it.
yeah, I mean, I'm trying to read the last inequality here. So if I know A and B, and I can describe U and V, this gives me X up to the intersection point up to R minus T bits.
Correct, yeah.
Yeah, more or less, I agree now. Yeah. So in T is this, well, in T is like, uh,
T is negative log of the difference between A and B and U and V.
so basically the angle, how small is the angle?
Yeah.
Well, if
How
it's
small is the angle?
2 to the minus T, then it's, well, okay, yeah.
And
And you have AB in the oracle, but actually you need what you need is only finite part of this AB up to R bits.
and another
What I don't understand actually why there are two indices, two subscript to or what does it mean R minus T,
Means
comma
that
R?
this even I can explain.
Yeah, what is that?
That means that the condition you take with R bits of precision and the
Ah,
X you take with R minus
okay,
T.
but on the right side we have only one
It's
somehow.
because it's the same, so it's like
Okay, but philosophically it should be clear.
philosophically. Yeah.
Yeah,
Okay.
okay.
yeah. Okay. Okay, so I'm going to use this geometric lemma a lot, but from here we start getting to the other half of the argument. So I can
That's a
continue,
half
or
argument. It's only very optimistic. Yeah. Okay.
okay. So so as a warm up, we'll assume. So let x be and here be in 0, 1, which is random relative to AB. Okay, Martin-Luff random, whatever you'd like. I just need the dimension of x to be 1 relative to A and B.
And what do we assume about the dimension of line?
For now, nothing. For now, it can be anything between 0 and 2. And so I claim. So the claim is for all sufficiently large R, the complexity of the point on my line is up to some sublinear additive term. In fact, it'll just be a logarithmic term. The complexity of the point is equal to 1 plus dr where again, D is the minimum between 1 and the dimension of the line AB. Okay, so this is the analog of something that Sasha did, I guess, 3 weeks ago in the finite field case. So I'll show you how this goes when we're dealing with Euclidean, the Euclidean field. Okay. So
so you can have dimension smaller than 1 or greater than 1. It's all covered, you say.
Right. And this, you should think about this as saying that so the complexity of the point is maximal. It's the most it possibly could be.
So we just need to show the lower bound on the complexity of this.
Yeah. Mm-hmm. And so actually what we'll show, we'll turn this into the following. So it suffices to prove that, okay, the number of bits I need to compute the line and the point x given my point is at most the complexity of the line minus dr. Okay, so just to be clear about why this is sufficient, notice that by symmetry of information, this is equal to the complexity of ABX minus complexity of the point, which in turn is equal to the complexity of the line plus the complexity of the point given the line. And from our assumption, this is R. So I didn't do anything here. I'm just saying why this is sufficient.
Okay.
Okay. Okay, and now
so I can you so complex it sufficient to prove that this thing is at most complexity of the line minus dr. So because then
So
what is R?
R is the precision. And since x is random, the complexity of x given the line is maximal. It's R bits.
Okay, and then C air of AB goes away, and we obtain 1 plus dr. Okay, yeah.
Mm-hmm. Okay. So I want to prove the starred inequality. And the way you should think about this is I'm given my point, so my algorithm, my computer is given the point x, ax plus b, so it's given the point on the line, and I want to find the line I care about. So what I'm going to do is enumerate all lines that pass through this point and choose the one that I want. This is essentially what we did in the finite field case as well.
Right.
So let S be all the dyadic rationals at precision 2 to the negative r, such that, so all the dyadic rationals, let's say uv, okay, such that ux plus v minus ax plus b is less than 2 to the negative r. So that's the first condition. And the second condition is I want the complexity of my candidates, uv, to be at most my pen's dying. The complexity okay. At most the complexity of my line. Okay. So the point of S is that these are the candidate lines that I'm searching for. So S is enumerable. Given x, ax plus b.
So in the left-hand side, you probably also have finite precision complexity.
Yeah, so U and V are the dyadic rationals. So so it's enumerable, and importantly, AB is in S. And when I mean AB is in S, I mean a dyadic approximation of A and B are in S. Hence, the number of bits needed to describe AB is at most log of the size of S. So the usual Kolmogorov complexity, if the point I care about is in an enumerable set, then the number of bits needed to describe that point is at most the cardinality, log of the cardinality.
Yeah.
Okay. Now, let UV be in S such that the complexity of UV given A, B, and given X is at least the cardinality of S. So choose one from this set randomly. So the situation that we have right now, we have the line we care about, AB. We have this other line, UV, and they intersect at the point X. I'm now going to apply the geometric lemma to this pair. So, by the geometric lemma,
and wait, but so our task now is to upper bound the logarithm of S by the expression that was this complexity of AB minus dr.
yeah. Yes,
So
exactly.
you take UV of maximal complexity from this set S, random, uh, but it's like also should be independent of A and B, or in some sense, like why you don't take just A and B?
Well, it's always better to give more information if you want, but I want to choose U and V, which is maximally complex relative to A, B, and X in this set.
Ah, so A, B might be, well, they should be probably maximal complexity, but okay, yeah.
Well, we're conditioning on A and B. So if A and B is the maximally complex line in the set, then the set is a singleton,
Ah,
basically.
okay, yeah.
Yeah. So now I just plug these things into the geometric lemma. So let's see. So I have um, okay. So I need to be careful with my precisions here. Okay, so if I know my line AB and I know the line UV, then my geometric lemma says that I can compute their intersection to precision r minus t. And of course, if I know UV, then I know UV. So again, I know AB, I compute UV, I get X, and I get UV. Okay? So now I guess we can deal with the left-hand side because it's easier and it's just several applications of the symmetry of information and the assumptions. So the left-hand side is plus CR R minus T R UV X. Okay, so I applied symmetry of information to the left-hand side. I guess this is actually just equality. Equality. And now, by my assumption of X, X was random relative to AB. So conditioning on AB does nothing. This is still maximal, R minus T. And now the complexity of UV given X and AB. The way I chose UV was that this was at least log of the cardinality of S.
Yeah, okay. So we need some bound on no, so we need some lower bound on the cardinality.
Oh, we want some upper bound on the cardinality.
No, but if we want to continue this inequality, we need some lower bound.
Oh no! So I'm done with the left hand side. I'm now gonna upper bound the right hand side.
Ah, okay.
Okay, so that's one, and then the other one is okay. So first of all, so U and V. So we know that UV and AB share the first roughly t bits. That's their distance. And of course, more information can't increase complexity. So okay, I did it again. Okay. Knowing more information can only decrease complexity. Symmetry of information.
But why is there no longer A?
Yeah, so I just wanted, so this step is just to apply symmetry of information. So I'm saying I'm throwing away the information of the tail bits of AB, and I'm only looking at the first t bits, which is the same as the first t bits of UV.
Yeah. Okay, yes.
So symmetry of information, it's this. And now notice that because of the way I defined S, the complexity of UV at precision R is at most that of AB. That's by item 2 of my definition of S. And now, sorry?
Yeah, sorry. Yeah. Yes.
And now, again, I'm using the fact that the first t bits of UV are the same as the first t bits of AB. So this is actually the same as that. In other words, combining these inequalities, we see that the thing I care about, the cardinality of S, is at most the complexity of AB minus the complexity of AB at precision t minus R minus t. And I claim that this is less than what I wanted, which was, recall, I wanted this to be less than CRAB minus DR. Which is equivalent to, how do I want to do this? Maybe dr minus r is less than or equal to CT AB minus t. And this is true. You can check. So should we check or?
No,
Yeah, I mean, so once again, so so D is just, so in one case is just the dimension,
Yeah.
and this is lim-inf. So
no,
this
this is exactly what bothered me, because before my previous, as I thought before that we cannot do these things on the level of dimension of finite approximation, and on the level of finite approximation we get something worse. And now you mysteriously get the good bound bound on the level of fine approximation, which I believe to be completely impossible. So there is some error in my former belief probably, but I should think to understand why I made this error, because at that time it was convincing. But
Yeah, so Sasha, you're just saying that you want to understand to finish to understand this derivation.
no. I just saying why it sounds very strange for me, because no, this is a kind of argument which I can which is done on the finite level and more or less corresponds to what we did with finite fields at some extent.
So
But somehow I was convinced that it could not give the desired result. But now I am confused. But of course I should recall why I was convinced and see and look at this argument again. But this is my problem. Don't worry.
yeah, I would like to understand, I mean, at least to finish, to understand this line by line, this derivation.
Yeah, sure.
So, I mean, so let me just recall. So if dimension is less than 1, then D is just less than 1, and this is a dimension.
Yeah. So if D is less than or equal, so let me strictly less than 1. Well, let's do it this way. Let's say that
But
the first
what
case,
is the relation between T and R? What is larger?
R is always greater than T.
Mm-hmm.
R is always bigger than T.
T is the loss of precision and R is precision somehow.
Okay, so we need to, so we have this upper bound on log S, which is the complexity of the first R bits minus R.
Then, because R is larger than T, the left-hand side is less than the right-hand side, because here we have also D, actually, dt in the right-hand side, dt minus T. Mm-hmm. And it's clear that dr minus R is less than dt minus T because R is greater than T.
Mm-hmm. Mm-hmm. So
Nikolai continues, you understand the inequality. Why it's
I understand the inequality, but I don't understand many lines before.
No, so but can you explain the last inequality? So we have to show
Давайте я быстро было по-русски. Ну, в правой части стоит dt минус t. Это понятно?
Нет. Подождите.
Ну,
где dt? Нету никакого dt.
c с индексом t от AB это d умножить на t.
Ну, это не совсем так. Это лиминф. Там, знаете ли, может больше быть, чем это.
Так нас интересуют только эти элементы, больше ничего. Ну, примерно dt там будет.
Ну, хорошо, если это просто dt, да. d на r минус r, d минус...
So the question is whether we consider not arbitrary R, but some R for which lim-inf is achieved.
We don't need to do that. No. R can be anything. Notice these things cancel.
Yes.
So the only thing I need to check is this.
dr minus r is less than CTAB minus T.
And I claim that it's true so long as T is above epsilon r. Notice, so since r is sufficiently large, if T is greater than or equal to, say, epsilon r, then CT AB is always times T minus, say, epsilon T.
So for large T, the complexity of T approximation is bounded by dimension.
Yeah.
Is lower.
So the upper bound is D times T minus T, and because T is it could only be smaller, this is the negative number, so okay. And if T is some constant,
Yeah. So if T is
and probably it's just a constant. So I mean, it's just you need that.
so yeah, so we need to handle the case when T is small. Now, what you do,
But you can't just say that it's just a constant. The upper bound is like basically zero, and the left-hand side is negative or zero. I mean, so if T, I mean, so there is some. So I mean, this upper right-hand side, CT of AB minus T. So if T is like bounded by some constant and it's just constant, we are interested in a moment starting from which the limit, I mean, then the limit is at least D is so that every value is at least dt minus epsilon t. So if we before this moment, the upper bound is the right hand side is just zero and the left hand side is non-positive, like something like that. You can say probably or not.
Sasha, assume that our dimension is just the limb, not limb sup, not limb. Assume that we are given that the limit exists. Is it clear, the last inequality?
Yeah, I mean that's what I'm saying. If it's or it's constant or it's small compared to just.
In the second case, the left-hand side is zero, the right-hand side is non-negative. So it's trivial, right?
Yeah.
In the case, in the first case, the left-hand side and the right-hand side are d minus 1r, d minus 1t, and r is at least t. So also it's clear, right?
Yeah. I mean, you just have to say in something that if, this you assume that t is like also goes to infinity here. But it could happen that you have a large r, and then, but for this large r, you have a very small t. But then then you just say that the left-hand side is just a constant, and the left-hand side is non-positive. So it's fine.
Yeah, in fact, as long as T is a sufficiently large number, it can be larger than an absolute constant. It will always satisfy this because of the limit.
Yes.
So, yeah, so we just need to make sure that T is bigger than an absolute constant, which we'll do up here. We just say, I'm going to give the first absolute constant number of bits of AB, and I'll restrict my lines to everything within that. So it's a small modification on the definition of S to make sure that T is always always sufficiently large.
I see actually another very subtle point in your argument. Mm-hmm. So you use the notation C, R minus T, R, R. Do you assume that R minus T is applied to X and RR to U and V, right?
So here, yes. So you're talking
So,
about here?
so, for example, here, what do you mean here? UV, X, A, and B. What is applied to what?
So I'm saying this line here, I'm trying to, so it's the complexity of UV to precision R. So the number of, the amount of information needed to get the first R bits of UV, knowing the first R minus T bits of X. So that's the R minus T. And knowing the first R bits of AB.
So, okay. So you say that actually in all your notation, when you write the indices, lower subscripts, you actually mean the first R or R minus T bits of corresponding strings, all right? Then
Yes.
it's not clear what means the complexity CR minus TR of X given AB. So now here you have only two subscripts and three objects. What does it mean?
I think about AB as a tuple.
As the tuple, and
so R is applied to AB and R minus T to X.
I'm sorry, my computer died.
So
Yeah,
then to verify everything here, we need actually to add these indices, so these subscripts, to the string they belong to. Otherwise, it's not clear how to use this symmetry of information.
let me add the parentheses. So is that better? Because it's saying the complexity of the object, which in this case is an element of R2 up to precision R.
No, I guess we need to try to repeat the manipulation ourselves and to see whether we are able or not, and maybe looking at the recording when needed. So, no, it seems to me that we somehow almost repeat the finite case argument, and still. So, but in the finite case argument, we have actually two subcases when d is greater than 1 and d is smaller than 1.
Yeah.
And for d is greater than 1, there were some additional complications. And here you think there are
no. Actually, Sasha, no. This is the warm up. This is taking full advantage of the fact that X is random relative to A.
So you now get the upper bound of complexity, yeah. So
Yeah.
you get the right point of the interval.
Right.
This we already do for finite case, and still we have some problems, some differences in argument when d is smaller than 1 and d is greater than 1. I don't know.
No, I don't believe we did. No, it was when we wanted to have the X
Somehow
variable.
you united them.
So
in the case, the difference was in if complexity of line is smaller than 1, then line can be reconstructed from at its random point. And if the complexity is greater than 1, it cannot be exactly reconstructed. We needed the complexity. We need to estimate the complexity of reconstruction, which is not 0 now.
right.
But you somehow you combine this in one argument, or
So I think you can do the same. So if you go back to the finite field case, yeah, I think that would be a good go to the finite field case and
see what is happening.
And combine the two cases only when your X coordinate is random. Only because when x is not random, then
very random with respect to whatever we need. Yeah.
Right. Yeah. So this is so the case when x is random, we get sharp bounds on the dimension of the points. But this relied heavily on the fact that x was incompressible with respect to the line.
So what we have proven is just the right point of this interval.
Right.
So maybe we should stop here for now, and we will try to study what you said, and to be really sure that we understand what is happening.
Mm-hmm.
And then maybe you can then explain the next part.
Sure.
Yeah, because
you can say that in the so if in a finite field case, you somehow also should consider the number of bits, or I don't know, because here I don't know.
In finite field case, I think this loss of precision shouldn't appear at all.
Right.
No.
And then, at some points, what we are doing, something we said, okay, like the first t bits of AB is the same as of UB, and then we replaced it back.
Mm-hmm.
So
we don't have to do this. So this is just for Euclidean space because we're dealing with approximations. In the finite field case, two lines determine a point exactly. So we don't have to deal with any sort of precisions or anything.
We can let t equal to 0 in all the consideration, you say.
Right. Yeah. I think the finite.
Okay.
I guess this is the exercise that we should do before our next initiation session. Because now something is strange to me, but okay.
Yeah, I would definitely try to do the finite field case of this in one statement. I think you'll see what's going on, and in fact, the Euclidean geometry isn't causing too much of a problem here because we're dealing with lines.
That's what I can't believe, because I even thought that I understand what is the problem, but now I am confused completely. With this, there was some kind of square root in this bound for the area on the sphere, and this was the source of the problem.
No. But spheres are curved, so the main point is that we're dealing with lines. So Euclidean geometry can be really nasty for these problems because we're dealing with approximations. But the general the moral of the story is that if your objects are linear, if they're lines, the approximations aren't so bad. They behave a lot like the discrete counterparts. When objects are curved, like spheres or polynomials or something.
Spheres are actually just two-dimensional planes in 3 dimensions. It's projective space, and it should not be that bad. I cannot. I see that there is a problem in my understanding, so I should think more.
Sasha, think about this. If you have just even in R2, you have two circles that are tangential, so it looks like a clamshell.
Yeah.
Now think about if you look at the 2 to the negative r neighborhood of those circles; those are annuli. The diameter of the intersection of the annuli can be huge if they're tangential, like root 2 to the negative r. This is a big problem.
But still, if we are considering dimension of something, then the something is either you can project the sphere to one of the standard planes and reduce everything to plane, not changing the dimension. So
I think that might be an issue. If you get rid of the curvature, then probably something's gone wrong because the curvature is somehow really important. It's causing a lot of issues that we can't get rid of.
Okay, so let us digest this. Thank you very much. And